Hello everyone, my name's Logan and welcome back to the lecture hall. Today we're covering section 5.3, the fundamental theorem of calculus. This is our third lecture for the UCI Math 2B single variable calculus course. So let's get into it. What is the motivation behind the fundamental theorem of calculus? Well, it is the connection between integrals and derivatives. What do I mean by this? Well, because integrals and derivatives are inverses of one another. So we can prove this with the fundamental theorem of calculus. So FTC1 states, because there's two, there's FTC1 and FTC2, they're both parts of the fundamental theorem of calculus. FTC1 states that g of x is equal to the integral from a to x of f of t dt. Okay, and this is where a function is, where f is a continuous function on a to b and x varies between a and b and g only depends on x. Well, what does that mean? That means x is in between the interval a to b and the function g of x only deals with input values from x, right? So let's kind of look at this. Let's say our g of x is the area under the curve. Well, we see that g of x plus h minus g of x is approximately h times f of x. Well, what is that? Well, this is just this area right here, right? Because this is g of x plus h is the right bound, right? And then g of x is the left bound. So this is this little area right here. Okay, and then we know that the distance between these two is h, and then we know that f of x is approximately the height. So we're saying that the width is h, and then the height is f of x. Well, how can we change this a little? If we were to just divide by h, and divide by h, now we get something that we've kind of seen before. We see g of x plus h minus g of x over h is approximately equal to f of x. Okay, that almost looks like the definition of our derivative, but we need a limit. So then, let's take the limit. Well, we see that if we take the limit as n approaches infinity of g of x plus h minus g of x over h, we get that this is equal to the derivative of g of x. And we also see that it is equal to f of x. So, what is this telling us? This is telling us that the derivative of g of x is going to be f of x, right? And so that's saying that integration and differentiation are inverses of one another. Integration is kind of moving backwards, and differentiation is moving forwards. And that's how you can kind of look at the two. So now we have the official FTC1 and FTC2. If f is continuous on a to b, then the function g is defined by g of x is equal to the integral from a to b, or from a to x of f of t dt, where x is in between a and b, and it is continuous on a to b. And g prime of x is equal to f of x. Alright, perfect. Now we have FTC2. If f is continuous on a to b, then the integral from a to b of f of x dx is equal to big F of b minus big F of a, where f is the antiderivative of f, of little f, such that f prime is equal to f. And then we get another result from this. We get big F of x is equal to g of x plus c. And why is this? Well, this is because f prime of big X is equal to g of x plus c, and then you take the derivative. And then that is just equal to g prime of x, right? Because this c is just a constant, and when we differentiate a constant, it goes away. So then we get g prime of x, and we know that's equal to f of x. So our general form for an antiderivative is g of x plus c. And this is because constants go away. So we have no way of knowing if it's really big F of x is equal to g of x plus 7, or g of x plus 4, or whatever it may be. So you always slap that plus c on at the end whenever you do an antiderivative. So this is the fundamental theorem of calculus, because integrals and derivatives are fundamental after all. And this is all I wanted to cover in the lecture portion of the video. Let's transition to some practice problems. Alright, now onto the practice problems. We're doing number 7, 11, and 23. So, let's jump right into it. What are we supposed to do for 7 and 11? All it says is find G prime. And we do this with the fundamental theorem of calculus part 1. So what do? Well, we just do G prime and we just take this, right? We see, oh, this is just an x. So then we're just going to plug it in, and then we'll see that G prime of x is just going to be equal to the square root of x plus x squared. Is it really that simple? Yes, it actually is, because we're just dealing with an x term here. If we see something a little bit more complex, we see, okay, we want to find the derivative of big F of x, and this is equal to the integral from x to 0 of the square root of 1 plus secant t dt. Well, this kind of messes us up, because fundamental theorem of calculus only works when the x is up here in the upper bound, but it's down here now. Well, we know a property from last video, I believe, that this is equal to the integral from 0 to x 1 plus secant t dt, right? And then we just make it negative. We throw a negative in front because we're swapping the bounds, and we make it negative. Okay, well then that's really easy, because now we just throw this negative in here. And then we find that f prime of x, I'm doing it up here because I ran out of space, is just going to be equal to, well, shoot, man, we just plug the x into the secant t. Okay, and we just get f prime of x is equal to negative, because we cannot forget about this negative, square root 1 plus secant x. And that is our derivative. And FDC1 is actually really nice because we can just kind of be like, oh, there's an x, boom, and we just plug it in. Of course, if we had something different, like if that were to say be 2x, we could plug in the 2x's here, and then we would also have to multiply by the derivative of 2x, which is 2, right? So that would be 2x, that would be 4x squared. And we multiply by 2 because when you do it, it's kind of like chain rule. You had to do the derivative of this 2x as well. But that's besides the point. Okay, now it says evaluate the integral from 1 to 9 of the square root of x dx. Well, let's rewrite this. 1 to 9, well, that's x to the 1/2 dx, right? Okay, cool. Now what we have to do is we have to do the power rule, but not the power rule of the derivative, the power rule of the integral. So we're going backwards. So what do? Well, we add 1 to this, right? Because normally you subtract 1. We add 1, and then we want to make it so that the derivative is just equal to the x 1/2. What do I mean by this? Well, what we're going to do is we're going to do x to the 3/2, right? Because we add 1 to the 1/2. And then we multiply by 2/3, right? And then we do solve from 1 to 9. But this may be confusing. You'd be like, where do you get the 2/3? Well, if we were to differentiate this x to the 3/2, 2/3 x to the 3/2, well, how do we do that? We do power rule, so we bring this out in front, right? And then we subtract 1, so we bring the 3/2 out in front, and this is equal to, if we were to do the derivative, this would be equal to 3/2 times 2/3 x to the 1/2, right? And that's our derivative. And then we see this cancels with that, and that cancels with that, and we're just left with this x to the 1/2. And then, hey, that's what we have right there. So we know our antiderivative is correct. So don't worry about that. And now we have to solve. How do we solve? Well, FTC2 states that we plug in this number and subtract it from this number. So it's going to be 2/3 times 9 to the 1/2 cubed, okay, minus 2/3 to the 1 to the 3/2. Well, the reason why I put this square root 9 and then cubed is because this is easier to deal with, and I just did this for 1 because that will just always stay as 1. So, what is this? We do the square root of 9, which is 3, and then we cube it, which is 27. Okay, so then what we get, this is equal to 2/3 times 27 over 1 minus 2/3 times 1, because 1 cubed is 1, square root of 1 is 1, so then this is just minus 2/3, and what can we do? Well, let's just multiply those two. So we get that's 54, right? 54/3 minus 2/3 is just equal to, well, what is it? 52/3. And you can just leave it like that. And that is our answer to the definite integral from 1 to 9 of the square root of x dx. And so we are going to do a shitload more of integrals, pardon my language, but we are going to do so many more integrals in the next few videos. So if you're not totally convinced on this power rule yet, that's okay. We're going to deal with a lot of antiderivatives, and you guys will see. So that is all I wanted to cover for the whole video. Again, my name was Logan. Thanks for watching. Have a great day.